And then next going to share our screen. So go to here. Okay, so last class, I remember we started the dimensionality reduction discussion, okay? And we also went over the difference about feature selection, because previously we discussed feature selection. And over here is dimension reduction is more about feature extraction, okay? And because for feature selections, you're going to maintain the original feature, but among the number of features, you pick the most important ones. And the feature extraction is you are going to also transform or project the feature into a new feature space. So that's a major difference. And I remember we also briefly discussed the three major methods for dimension reduction and feature extraction. It's PCA. We just started the PCA, okay, principal component analysis. And this is quite useful because it's can be used for unsupervised data compression. So it's not just for dimension reduction and the feature extraction. It can also be used for data compression. Okay, later on we are going to see in detail about in our example. And the second one is called the LDA. It's linear discriminant analysis. Okay, so today we will also discuss it. The third one is kernel PCA, and the kernel concept previously in SVM we also learned. Okay, so first let's go over the concept about PCA, okay, the principal component analysis. So the major idea here for the dimensionality reduction, because here we discuss, we mentioned it's about dimension reduction. Is it? So how do you achieve that? So basically a lot of times is you do, so you transform the feature space. Transform the feature space. Okay, so how do we achieve that? So let's take a look like in this example. So previously, suppose you have the feature x1, x2, is it? So this is the feature space. Okay, horizontal and vertical, is it? And then you have some samples. Is it? Those samples, you have star, and you also have a circle samples, and you also have the square samples. Is it? And through this diagram, this figure, we can see if you pick some feature space, it looks like this, like U1 and U2, like this feature space, is it? And if you project this of the data onto this feature space, if you project off those data or the circle one or the star one, is it? And you can see it's quite, the data quite separate well. And also along this U1 axis, so this bunch of sample point versus this circle bunch of sample point versus the square ones, they spread largely. And they spread quite largely, is it? So what this means is they have higher variance along this axis. And we can also kind of see it's basically separate very well. Separate quite well, is it? And all we want to do here is do the classification, is it? Find out which class, is it? Then in this case, if you pick this new feature space, then you can see, oh, They can be separated quite well, is it? So this is along this U1 axis. But if you pick the other one, U2, then if you view it, if you do the projection, like the vertical data and the circle data and this star data, is it? And then you will find they are not spread. Not spread well, is it? They are all kind of crumbled together, is it? So if you want to separate data, separate among them, it's not that good, is it? So that's this analysis. And the same thing if you take a look along the previous feature space, is it? It's also not as spread as U1. Is it? If you compare V1 and X1, is if you compare these two, and the X1 not spread as good as well as what? As U1, is it? So they are not spread as well as U1. So from what we just visually see, U1 can have your data, when your data projected onto this axis, the data, the sample data can spread quite well, is it? So this is the concept of principal component analysis, okay? And the principal component, so basically over here, we see this U1, basically it's what? It's a principal component. It's our principal component. So that's how this comes from, principal component, okay? And what's the PCA's goal? So PCA's goal is to find the orthogonal component axis with maximum variance, is it? So maximum, and we just see this U1 will achieve the goal of maximum variance because of the data it's spread widely, is it? So that's the key point here, okay, about PCA. So why you pick that component as your axis, is it? Okay, and as I said, with this PCA, then we can convert the original like X1, X2 feature space to, you just use that a single principal component. You can also achieve the goal to separate the class, is it, to find the class. And here it also explains why U1 is better than U2, is it? Because sample to U1's distance close enough. That's one advantage. Second, when you do the projection, we just see U1 separate the data much better, is it? And how do you come up with the principle? So visually we can see it, is it? So there is some math derivation that you can use to find that U1 principal component. So the math background on it is you first need to find the covariance between two feature space. So in this regarding is our X1, X2, is that we call it Xj and Xk. Okay, because if you have more than two feature space, is it? And then what you can do is regarding the feature space, is it the two feature Xj, Xk, and with all of the samples, is it? And then you can come up with this covariance matrix. Okay, this covariance matrix. And with this covariance matrix, and here D is a number of features. So this is regarding the original. This is regarding the covariance matrix of your original feature space. Okay, original feature space. So you find the, and And how do you calculate the covariance? You use this formula to find the covariance between any two features. Okay, any two features. So that's the idea about the covariance calculation. And in math, then how do we find the maximize covariance component, is it? So here is a bit, the math behind this is quite comprehensive. So here just give you some brief idea. So we have a concept called eigenvalue and eigenvector, okay? And you have that matrix. So in math, if you have the matrix, and if you can find the matrix, so here is a vector. So this vector times this matrix, and basically it is some constant value also times the matrix. So if you can find the number and the vector regarding regarding this matrix, is it? And if you can achieve, make those make this equation, then what you say, you find the pair of eigenvalue and eigenvector. Okay, so in over here is we wanted to know our eigenvector. So this eigenvector is going to be our principal component. So in our diagram, it's that U1. Okay, so use that, you can find this U1 eigenvector. And once you have this eigenvector find out, then you can do the projection, is it? So that's the idea of principal component, and how do we find the principal component, is it? And then the next concept is with this your eigenvector, it may not be a single one. Okay, you may have you may find like a number of eigenvectors that can make this equation be true, is it? Then in that case, how do we pick among of the eigenvectors? How do we pick a k number of eigenvectors, is it? And the total feature, you have d, is it? So this is going to be less or equal than d, is it? But generally speaking, because here what we care about is reduction, is it? You wanted to do dimension reduction, is it? So the k, generally speaking, is less than d, is it? So that's your goal. Okay, so normally what you can do is you can define certain threshold. You said, I want to keep a certain percentage of the variance. Okay, and then what you can do is you just use the eigenvalue, is it? Here is a summation of the eigenvalue, is it? So this is regarding all of your original feature space, is it? And you said, okay, I'm going to try out, is it? If I use one eigenvalue, will it achieve? If I use two, I sum them up, will that achieve? Is it? Suppose you define, okay, 99%, I want to retain the variance, then the threshold is going to be 99%, is it? Then you can find the number of the eigenvectors and eigenvalues. You sum them together, that will reach this goal, okay, reach your threshold. Then you can just keep those eigenvectors and those eigenvalues for your principal component, okay? So that's the math background behind the principal component. And in our previous units, we also learned random forest. Is one of the a nice feature for random forest is it will give you the feature importance, is it? Then you can use the feature importance parameter to pick up useful useful features, is it? So basically here it says random forest, you can use class membership to compute the node impurity, is it? We can use random forest to do feature selection, okay? And over here, you see it's different concept, is it? Is you have the feature space, then you transform the feature space into a new feature space. Is it? With this new feature space, after you project, you may also reduce the number of features, is it? That can be used for your model training, is it? So here, so the original you have D features, is it? And here you reduce it to K number of features. And it's also in the new feature space. So this is the idea about the principal component, okay, principal component. And after you find out the eigenvector, is it? That's what you find out, the eigenvector, and then you can use the eigenvector to build this projection matrix. So this is our projection matrix. Is it? And you use this projection matrix, once you find it, then you can use it to find out the new principal component, and you can transform your sample data, is it, onto this new new sample space. So you can do feature transformation. So over here, this part shows feature transformation. Feature transform. Okay, so we can achieve that. Okay, and then what next? Some advice on applying principal component analysis. Okay, one of the major uses is for compression. Okay, and later on we will see our example, especially a lot of time if you want to apply it for image machine learning. Okay, this can be one of the useful tools, because it can reduce memory disk space. So you can reduce memory disk needed to store the data, okay? So that's one of the nice thing. The second thing, because you reduce number of features, so of course you can speed up the learning algorithm, okay? So that's one of the nice thing. The other thing, it's also good for visualization because you reduce the features, the number of features. And if you want to visualize, it's more visible. And here it says it's not recommended to use PCA to prevent overfitting, is it? And the overfitting previously we discussed, we said you use L2 regularization, is it, to penalize the weight scale. So we use L2 to do the regularization to prevent overfitting. Okay, so just keep those in mind. But here it says normally you can try to running with original raw data, is it? And if result is that doesn't do what expected, then you can consider use PCA to do transformation. Okay, so that's one of the features, recommendations for us to use with PCA. So we have the concept of PCA. And next, let's see, share screen. Let's take a look at the next one, okay. The next one is about, I need to minimize. Where is it? Okay, so the second one for dimension reduction is LDA. Okay, we mentioned previously. So LDA, its complete name is called linear discriminative analysis. Okay, so what is the concept behind this? So it's also going to do feature space. It says it's also going to find the feature space. And but the goal here is, be careful, a little bit different, okay? Is to optimize the class separability, okay? And the PCA's goal is to try to find the orthogonal component that's going to maximize the variance. So these two are different, okay? So be careful. The major idea behind these two. And it said the linear transformation technique, it can be used to also to reduce number of dimensions. So here it also involves, you're going to reduce the number of dimensions. So let's see, take a look at the idea. And also for LDA, it can be used for supervised learning, okay? And for PCA, it can be used for unsupervised. So that's also a major difference. And also here, there is another difference is regarding when you apply to LDA, the data normally, it says normally distributed data. Okay, then it's going to be quite helpful if you apply LDA. And here it shows the idea, is it? So you have one group of data, you have the other group of data, is it? And maybe your previous sample space looks like this. Is it maybe that's your previous sample space? Is it? And with the previous, it's not that, you know, visible, divisible, is it? And over here, we find this new component, is it LD1 and LD2, is it? And with this, you can see it's quite divisible, is it? And also over here, we said the data needed to be normally distributed because based on LD1, for all of the distribution of the data, it's normally distributed, okay? And for this, it's also normally distributed. And even if you pick LD2, it's also normally distributed. Is it? Because it's normal distribution, okay? And we can apply this LDA. And it's normally distributed, but here, let's take a look. When you project the data onto LD1, it's quite separable, is it? Because you can visually see that all of the data is going to be projected on this cluster, is it? And for the other one, it's going to be distributed on this cluster. But if you projected them to the LD2, then it's not separable, is it? Yeah, so for so for linear discriminant analysis, the goal is we need to find this LD1, is it? And the vertical one, LD2, is it, regarding this new space. So how do we find it? Here there is, if you take a close look, you will see, is it? So regarding this bunch of data, is it, regarding this bunch of the data, so this is in class. So all of those data is within the same class, is it? And within the same class, they follow a certain way to distribute it, is it? And you want this same class of data, when you pick this axis, LD1, they will be as close as together, is it, when you do the projection? So they are very close to each other when you project it onto this LD1, is it? And between the star and the circle, they are interclass. Those are interclass, is it? And this is interclass, so between different class of data, is it? Between different class of data, you want them to project it as farther away as possible when you pick this component, Is it? That's your overall goal, okay? To find the component you want to project. So that's the goal. So then over here, so how do we find those components? And when you do the projection, that can achieve the goal. Is it? Achieve the goal is to within the class, then they will be as close as together. When you do projection, okay, and outside of the class, when you project, they will separate as further away as possible, etc. So next, let's see the math background behind those, okay. Here says for each class, you first compute their mean vector. So that's pretty simple to find. Okay, you find the principal component. There's something disturbed me. So you find for each class you find the mean vector. Okay, that's kind of easy to calculate. Okay, for each of the class, you find the mean vector. So that's, so C here says represent different class, okay? D represents the number of features, is it? And then for each of it, you can, for each of the class, you can find the mean vector because you can calculate the mean values, is it? Okay, so we find this, the mean, we find the mean vector, is it? And then what next you need to do is we need to calculate intra-class scatter matrix. So how do we calculate that? You're going to use in-class mean. This is within each class, it's mean, is it? And each of the samples is from that same class, is it? And then you can find this scatter, so the distribution matrix, we can find this. So that is within the class. And then you can also find out the between class scatter matrix, is it? So how do you find it? So this is each class's mean vector, is it? And this M is the overall mean. So regarding all of the samples, is it? So then between class, so inter-class distribution matrix, you can also come up, is it? Yeah, so we come up with those. And then here it says you solve the generalization eigenvalue of what? So you use the inter-class scattered matrix, its inverse times the inter-class one. You get a new matrix, is it? And with this one, and you find the general eigenvalue, eigenvector problem. Okay, and with this, then we can find out the LD1 and the LD2. Okay, those linear discriminant component. And then you can project. So the remaining step is going to be similar as the principle. Once you find, then you can do the data projection. You can transform your data, okay? So that's the concept about linear discriminant analysis. So LDA. And the third concept is about kernel PCA. PCA, we already know, is it? So, but some of the problem is non-linear problem, is it? So to do the non-linear problem, how do we tackle it is you can project them into some higher dimensionality. So here, you may say it's contradictory with our goal, is it? Because your goal is to reduce dimensionality. But here, because the problem cannot be solved with linear way, is it? So then you can, what you first can do is you can project into some higher dimensionality space. to get your new feature space, is it? And with that, then it can become linear separable, is it? Then you can apply PCA. So this is a concept called kernel PCA. So the kernel concept basically over here, it's similar as what we learned before with SVM, as it project to some higher dimension. So you come up with some nonlinear transformation. And then, so that's basically just solve the part of problem. We call it a kernel trick. Is it? So you find some kernel function. So this is a kernel function. So previously you have x1 and x2, is it? And then you find some kernel function and you transform from the original x1 and x2 to this new mapping relationship, is it? So we call this as kernel trick, okay? And once you achieve the kernel trick, is it a kernel trick? And because for PCA, what you care about is covariance the matrix, is it? The covariance matrix. And the covariance matrix, then this time, it's not your original original feature space. You need to do the transformation, is it? So here, that's what we said, you apply the kernel trick, okay? So you can convert the original feature space is covariance matrix to this new calculation of your covariance matrix. Okay, so over here, it's you don't do projection first. So you basically do not do projection first. And then to find a new covariance. No, you don't do that. Is it? What you do here is you just directly go from this covariance calculation, you just directly apply the kernel trick. Okay, directly on the original feature space. Okay, and then in this case, then you will find the eigenvectors. Okay, for this transformed new feature spaces eigenvectors. And once you have that, then it's pretty simple to, so the remaining steps is just the regular PCA, okay? So this is the idea about the kernel PCA. So we already know what's the three major dimensionality reduction approach, how they works, the theoretical background behind them, okay? And the next, let's see some brief comparison, okay? It says, here it says supervised data compression via linear discriminant analysis, LDA, is it? Here it says LDA's purpose to find the feature subspace that's going to optimize the class separability. Okay, so that's LDA's major goal, okay? And versus PCA, both a linear transformation, okay? You can reduce number of dimensions. And when applies to unsupervised, LDA apply to supervised. But for LDA, just be careful. Whenever you apply LDA, its assumption is that data normally should be normally distributed, okay? And also the classes, they have identical covariance metrics and also feature independent of each other, okay? Because otherwise it's not going to be good to use LDK, okay? So keep those assumptions in mind. And we can also apply kernel PCA for non-linear mappings, okay? So kernel PCA says can help to transform data that is not linear separable, okay, onto new lower dimension subspace. Is it because over here we also use PCA. PCA can achieve the goal to reduce dimensionality, is it? And we tackle nonlinear problem by project them into new higher dimension feature space, okay? But it's not contradictory with the concept of dimension reduction because you're going to apply PCA to dimensionality reduction. So that's the general idea about the concept part. Okay, the next one we are going to go over is our examples. Should be there. Let's see. No, I need to stop here. I need to bring that up. Okay, so next let's take a look about how we apply PCA, LDA, and kernel PCA. Okay, and here we are going to use the data set from that UCI repository. Okay, and if you cannot find it, I remember I also have it on our course website. You can download it and just go ahead, load it. So we have the data frame. So this is a data frame loaded. And you can see it's try to use all of the features to find the wines class, is it? And the very first step we do as usual, we do split. We split data into training and testing part. And this part is also similar as what we already learned before. So you are going to do data scaling, okay? And so here we use the standard scaler and you transform, is it testing and training data. And what the next part is shows us the detailed steps about eigenvalue and eigenvector. And basically NumPy package, it provides how to calculate eigenvalue and eigenvector if you provide the matrix, okay? And here it shows you how to do the covariance matrix calculation because NumPy also provide you a function called covariance function. You can find then with your data, you can find the covariance matrix, okay? And once you have the covariance matrix, if you call NumPy's eigenvalue eigenvector function, then you can find its eigenvalue and its eigenvector. So here it shows, is it, all of the eigenvalues and eigenvector. And basically this eigenvalue, the number of eigenvalues is similar as the number of your features you have, okay? And what the next part shows is try to show the total explained the variance. And so here you will find, is it, find the cum sum, is it, the cumulative summation of the variance, okay? And over here, it does the sorting of the eigenvalues, is it? And here it shows us, is it? So over here, so this diagram shows us, so it's a bar. Diagram shows us the covariance ratio, is it? And you can say, okay, so the last couple of, they don't have a lot of covariance ratio, is it? And for PCA, our goal is to find the maximized ones, is it? So even from this diagram, you can see, oh, the first couple of, they play very important role, is it, the feature, okay? And what this step look like line, they told us the cumulative. So those are cumulative one. So come sum. Is it come sum? So that's why you can see the very end, it's almost reached to the 1. Is it because you sum all of them up? Okay. So that's the idea about that part. And then you can, so after you have eigenvalue and eigenvector, is it, and you can do feature transformation, is it? And here it shows us that matrix. And once you have that matrix, then you can convert your data, is it? You can project your data into the new components. So here it shows you project your data to the new component, is it? And after you do this projection, and over here it shows us visually of the data, is it? So from this you can see, yeah, this newly picked principal component, it does kind of separate the data kind of good, is it? Yeah, so this shows the detailed steps about regarding those mass, eigenvalue, and eigenvector concept. And next, let's see. So for PCA, sklearn also provide us to do the PCA. And the PCA, it comes from the decomposition package. Okay, so if you want to do it, you first need to call PCA, create a PCA object. And then similar, you do the transform. Okay. After you finish the transform, basically over here, if you try to get the variance-ish ratio, is it, you can just call PCA. It has a parameter tell you the variance issue. So basically give you the features importance, is it? And here it shows. So basically this is similar as what we saw previously. We use NumPy to calculate eigenvalue and eigenvector concept, okay? And what next shows is for your PCA calculations, you can also specify the number of components you want to apply, is that in this case? And so over here it said, okay, I'm going to pick a 2 component, is it? And here it shows the result, okay? And with the PCA, so the PCA's goal here is to reduce the number of features, is it? And then the next, let's see. Next, so over here, we first said, okay, we want to use 2 components for our PCA. So you establish the dimension reduction with 2 component PCA, okay? And once you get that, then for your data, is it you're going to project your data into these 2 new components, okay? After that, let's see, you're going to apply logistic regression to do the classification, is it? And this time, your logistic regression, so your logistic regression is going to be on what? On the data from your PCA, is it? So this is projected data, not original data. So here it shows, is it PCA's goal here is to do what? It's not to do classification training for you, okay? So the goal is to reduce the dimensionality, to have new feature space. That's its goal, to have new feature space. Once you have new feature space, then you can project data, is it? After you project data, you apply the logistic regression on what? On the new feature space, okay? It's not the original feature, it's the new feature space. And then in this regarding, your model training is on new feature space, okay? We need to keep that in mind. And then you can see after you apply PC with the new feature space, then we apply the logistic regression, etc. And you can see, yeah, it can classify quite well here. It shows us the result, etc. And this is a testing part, okay, for training and for testing, etc. So that's regarding the the example about we first apply PCA to reduce the feature and project the data into the new feature, and then you apply learning algorithm. Over here, it's the logistic regression to train your data, and then to classify them. And what the next one shows is to do the LDA. Okay, so LDA, you can also find it in sklearn. Okay, so you need to import the module, and here it says, okay, I'm going to pick 2 components with LDA. Then same thing, you want your data to be transformed to LDA component, and after that, you're going to apply logistic regression also on this new projected data, and then you can see the LDA classification, So here is a logistic classification apply the projected data with LDA, And here we can see the result is also quite good, Can separate them quite well, okay? So that's logistic regression applied after LDA. And the last one shows using kernel, because some of the cases, like if you take a look like this kind of data, okay, like 2-moon style data. So 2-moon style of data. And if you want to apply the linear way to do it, it's hard, So over here, it applies the kernel PCA, okay? And after you apply kernel PCA, here it shows, Then it's quite separable, And then if you want to do some training, you can further do some training. But over here, the general idea here is to show is with kernel PCA, then it's quite efficient, After you apply it, it's even visually, You can view it quite well, the separability. That's why we also say, okay, PCA can also help a lot in regarding visualization. And then next one, we are going to show the next example. I need to bring that up. Okay, so the last example regarding the PCA application is regarding a very popular data set in machine learning regarding image, MNIST. Okay, so MNIST is, so we can take a quick look. It's all regarding image data. And the image data over here totally, and you can load the data from, so from from our pandas and NumPy, and sklearn, and so from sklearn, so MNIST data it's also comes with sklearn. And with sklearn data set, if you import the fetch machine learning data, if you do this, okay, then you can just call fetch machine learning data and you specify, okay, here I want to get to the MNIST. So MNIST is a number, it's over thousands of, over here it says 7,000 images. And the image is used to trace a digit number from 0 to 9, okay? So you have 70,000 of handwritten digit. And then you can apply the machine learning model after you train them. And you can try like with one of your handwritten digit, and it should have pretty high accuracy to recognize. So basically here it also shows us the image processing kind of concept here, okay? So anyway, we are going to load our data, okay? Load it's the data frame. After we get data frame, you can see this data, we have over 70,000, it's quite large, is it? And the feature you can also see, wow, the feature has over 700 of features, is it? So what are all of those features, is it? And here we also going to do the split as usual, and then nothing new. And here it shows us the first 5 rows of data. So this is the first 5 rows of data. So the first number is 4. Second number is 1, and then 8, and then 4, and something else I cannot see, blocked, okay? So anyway, so here you get to the first 8, 5, no, you get to the first 5 handwritten digit, is it, from the data set. And when you want to display it, be careful, okay? So you do the show, is it? But you show, you call NP reshape the image. So basically it's 28 by 28 pixels here. Okay, and here the pixels show some values, is it? So if you times this, this is that 784. That's how that comes up. Okay, so basically each of the 785 features, it represents something here. Okay, it represents something here. That's how it comes from. Okay, we understand that here it gave us some idea. So it gives you some number, is it? So like I just explained, so those, all of those are pixels, is it? And because these are colorful data, is it? So with color that ranges 0 to 255, is it? If you read all of this data, if you want, you can see it gives you the data. Is it basically, this looks like what? This looks like a 1. Is there something like that? Okay, and because you can see over here, the feature, we have 784. Is it too many features? Too many features, is it? So it's going to take a lot of space, is it? For the storage and also for calculation. So the way is here, let's take a look at PCA, because PCA can reduce dimensionality, is it? And here I said, okay, I want the threshold to be 95%. I want to preserve 95% of the variance, okay? And so you get the PCA instance, and then you do fit with the original data, is it? And after you do the calculation, then you can find the number of components. The new feature space, it's reduced a lot. Is it from 784 reduced to what? To 154. So you only need 154 features. Is it columns? Basically, the 154 columns of data to remember the digit, okay? And then we can take a look. So 154 basically over here, then it shows us, is it? So previously you have the original, so that's 784 components. Now you see it's 154 components, is it pixels? Okay, but with this, you can see, even though it's not as sharp as the original image, but it's still readable, is it? So it's kind of, okay, you get your image from high definition, is it, to low definition, is it, low definition image, but it's still readable, is it? So this explains. We also, sometimes we say it's image compression. Is it? Because your image is still viewable. It's just not as sharp as what the original one gives. Is it? So this here, the concept. So we apply with PC, you can also achieve the image compression, okay? And we apply PCA here shows the original is going to be 784 if you don't specify the threshold, okay? And if you specify the threshold, and it can be reduced. And here it also does different number of calculations of the threshold and shows diagram how it varies. And from the this diagram, the cumulative explained covariance, you can see when it reaches to certain number of principal component, is it like around 150-ish? Is it? It doesn't matter. Is it? It doesn't. So your explained covariance doesn't play a lot of role. Is it? So that's why you can drop them. You can drop them, okay? Because it won't impact too much about the training of your data, okay? So that's just explained the concept here. And what next it shows with different number of principles, the components, is it how accuracy they are going to be, okay? And here it shows the with different number of components, okay? It also shows the image effects, that. And with PCA, then after you apply it, you can do the logistic regression, is it, to do classification, okay? So we are going to apply logistic regression. And we first do the 95 threshold, is it, with 95 threshold, and then to give us some prediction of the data, is it, the original one and the testing one, is it? And you can see the result whenever you want to test a single digit, handwritten single digit, it's with 95%, the result is pretty good, is it? So what over next it shows is it the accuracy score, it's still above 90, is it? So the result is, it's not bad. Okay, so that's the